So we're talking about statistical inference, and in this video, we're going to talk about confidence intervals. A confidence interval is a range of values constructed from the sample data so that the parameter occurs within that range. In our previous video, we talked about a point estimate using a simple sample statistic. So if we look at the average age of 20 people, and then we use that average age to infer that the population, the average age is whatever that sample statistic number was. We're simply saying the average in the sample is the average in the population. Well, the challenge with that, of course, is that every time you take a sample, you get a different average, a different sample statistic, and we have sampling error, that difference between that sample statistic and that population parameter. So to take into consideration that the sample statistic is a random variable, that it changes, we'll do a confidence interval. We'll get a range. And when we do a confidence interval, we need to specify the probability associated with that. So the specified probability is called the level of confidence. Okay. So we could create a confidence interval, for example, that says we are 95% confident that the mean or average yield of corn from farms using integrated pest management is between 142.7 to 153.9 bushels per acre. So we have a range. That population parameter here, which is that population mean, is somewhere inside of that range, and we are 95% confident that that's the case. Okay. Alternatively, we could state this as farms that practice integrated pest management while growing corn have a mean yield of 142.7 to 153.9 bushels per acre, and identify that that is a 95% confidence interval. So if we are providing a range, we do need to specify the level of confidence. Okay. One more example before we get into where this comes from. We could say that we are 95% confident that the mean total cholesterol level resulting from a canola-based diet is between 9.3 milligrams per deciliter less and 17.2 milligrams per deciliter more than the mean cholesterol level resulting from a rice oil-based diet. So again, a range and the level of confidence we have in that range. So we're specifying for each what is the population parameter, the mean here, the total cholesterol level, and then we give a range for it and we get a level of confidence. Now, when we look at changes, so when we create these confidence levels, they can be for specific values like we saw previously. Here, this is the average yield is between these two numbers. So we're looking at a particular parameter, that number is between those two. But as we build confidence intervals and we do hypothesis tests, we can also look at the difference between two parameters. And so we can look at, for example, the change, or we can look at the difference. So in this particular example, we're looking at the difference between a canola oil diet and a rice oil diet, and looking at whether the average is different between the two. We could look at over time. We could look at, your weight this month, next month, and look at does the average weight loss or the average weight of the population, is there a difference between now and a different period in time? So when we get to hypothesis testing, for example, and same thing with confidence intervals, we can look at differences between population parameters. When we get to hypothesis testing, we'll look at, is that difference statistically significant? Okay, if your confidence interval and you're looking at a difference between your range includes 0, then that means that it could be that the difference is positive, the difference is negative, or there is no difference, in which case we're unable to distinguish a difference between them. We would look at the confidence interval, and if the range was, so we're looking at the difference between two, was all positive, then that would tell us that there is a statistically significant difference between those two groups. whether the range was included only positive numbers or the range included all negative numbers. So we'll get more into that later. I reference that a number of times throughout various videos. So we'll look at that range as we get to things like regression and multiple variable regression. Okay, looking for that confidence interval. Does it span 0 or not 0 when we're covering differences? All right. What do we mean by confident? So where does this come from? The level of confidence is the measure of confidence we have that the interval estimate will include the population parameter. So you're asking yourselves, well, why can't we just be 100% confident that we've covered the population parameter? Well, to be 100% confident, you either need a census where you have surveyed everyone, or you've done so many samples, you've covered everyone. Your sample is so big that it is the population, right? So those would give us 100% confidence. If you are not talking or gaining information from everyone in the population, there is a chance that you don't capture it. And in order to have 100% accuracy when you don't have all the information, your confidence interval will be extremely wide. Okay, so we want a narrow enough confidence interval that we can be somewhat precise as to what that population parameter or the difference between two population parameters truly is, but at the same time recognize that in order to be more accurate, it has to be wider. So we trade off between accuracy and that narrowness of the confidence interval. So think about a confidence interval like this. Here is our population, and it is our sampling distribution, right? So we've talked about before, here we create a sampling distribution. And we take an average, and the first time we get an average number here, next time we get an average number here, next time we get an average number here. The averages, those sample statistics, are random variables, and so because of that, they have a probability distribution function. According to the central limit theorem, if we have sufficient sample size, we can then say that the average of the averages is that population mean. A single point estimate would have sampling error, would be off. So we take into consideration, what if we took lots of different samples? Well, some of the samples you'll notice are outside on the wings. They are more extreme values. And so when we talk about a confidence interval, we're talking about giving a range between A and B that would contain that population parameter. Okay. If you want to be more accurate, right, then your range is going to be much wider because it's going to take into consideration more of that variability in your sample statistic. But too wide of a range isn't that useful because if we're going back to say here, the average yield of corn with pest management, let's say it's anywhere between 0 and 200 bushels per acre. Well, I can't really tell then if I should use this pest management system if the range is going to be so large. I need to know really what is the impact really going to be, but the sacrifice is that if we make this super narrow, we're not taking into consideration all these different possible sample statistics. And so there's an increased chance that we're wrong because we get the sample here that's out here, and maybe the population is more like that sample than it is like this sample. Okay. So when we say a 95% confidence interval, we mean that 95 times out of 100, the sample mean, so 95 of these out of 100 would be within this range, and that would give us 95% for our confidence interval. Okay. So a 95% confidence interval means that 95 times out of 100, the sample statistics selected from our population will be within 1.96 standard deviations of the population mean. In previous videos, you've heard me talk about the empirical rule, right? A lot. And I talk about how 1 standard deviation is 68%, and 2 standard deviations is 95%, and 3 is 99.7. Okay, so This is a rough estimate because really one standard deviation is 68%, but two, it's 1.96, not two. That is the 95%. And when we're talking about it's actually 2.58 standard deviations to get to the 90. You can't even see what I'm writing. 99%. So 68, 95, 99.7, that's the empirical rule. Actually, 1.96, not two standard deviations, gets you 95%, and 2.58 gets you 99, because why do you need this extra 0.7%? So this is coming from that standard normal distribution. Here's mu. 1 standard deviation, 2 standard deviations, 3 standard deviations. So majority of your data is within 1 standard deviation. 1. Can't write 2 today. 3. Almost all of your data is within 3. Okay, so if we have, and so general confidence intervals are typically 95%, 99%. A 95% confidence interval, 95 times out of 100, the sample statistic is going to be within 1.96 standard deviations of the population parameter. A 99% confidence interval means that 99 times out of 100, that sample statistic is going to be within, and the part you can't see because my face is covering it, is that 2.58 standard deviations. Okay. So that's where they come from. And they come from, where does this 1.96 and this 2.58 come from? Let's just open up our standard normal table and take a look. Okay, so where does this 1.96 and 2.58 come from? So let me just go to the standard normal table we've seen before. Just a reminder, this particular table, the way that it shows information is it's the area to the left of the Z-score. When we talk about a confidence interval, one, for example, that's 95%, we're looking at the center here being 95%, okay? The middle being 95%. Now, if I go to my standard normal table and I look up a Z-score of 1.96, 1.9 over to 6, I get 97.500. So a Z-score of 1.96 says everything to the left is 97.5%. Okay, well, what does that mean is over here in the tail, that's 2.5%. If I cut off 2.5% on the other side, then now I don't have 97.5% in here in the shaded area. Instead, I have 95%. So that 1.96 is because everything to the left is 97.5%. And if I cut off the equal tail on the left side that I have on the right, I have, so hard to read, I have 2.5 over here, I have 2.5 over here, between 1.96 and negative 1.96. So I got 95% in the middle. So 1.96 itself gave me 97.5. That means there's 2.5 on the right. If I subtract 2.5 from 97.5, I get left with the 95. Where did the 2.58 come from? Well, let's go to 2.58. 2.58, right? 2.58 is 0.99506. So if we were to draw this, and this is 2.58, then everything to the left here in the shaded area is 0.99506. Okay? What does that mean is on this side? Well, what it means is on this side is 0.005. Okay? Now, if I cut off, see if I can draw in a different color. If I cut off an equal amount of 0.005 from this side, then I'm going to take my 0.99506, subtract from it a 0.005, and what you get is, it's crapped out on me here. Come on. It does not want to write right there. Can I write here? Let's see. It's just being a booger. 99%. Okay, so you should see the 99% confidence interval. That means the middle is 99%, comes from the difference between a z-score of 2.58 and a negative 2.58. So that's how we're getting these level of confidences. They're based on the sampling distribution, a standard normal distribution. And I think my computer has froze. Okay, there we go. So that's where this comes from. This 95% confidence interval, this 99% confidence interval, it's about the center of that sampling distribution that has a normal distribution in order to get us the information. All right, where are we? Okay, a 95% confidence interval is an interval generated by a process that is right 95% of the time. If we were to replicate the study many times, and each time the reported a 95% confidence interval, then 95% of the intervals will contain the population mean. Some of them will not, and that is because, right, as we get different sample statistics, right, some of these X bars were out here in the wings, and so they are outside of that. Again, why do we then specify the level of confidence? Because we want to get a more narrow range, but we recognize that the more narrow range, so that we can act on it, comes with a sacrifice in terms of accuracy. Okay, so typically we look at confidence intervals 95, 99, sometimes 90%. If you have a smaller sample, then you've got to go with a wider confidence interval, which is going to be less accurate. Now, in reality, we are not going to actually take samples over and over and over again. We only take one sample. Otherwise, we would have just done a census and gotten information from everybody in the population. So we actually take one sample, but if we can know information about the distribution in the population, remember our discussion about if we have a normally distributed data in the population, then our sample statistic will be normally distributed, and so then we can use this information. If we don't have normally distributed data within the population, we talked about binomials, for example. If your sample size is big enough, your sample statistics, your sampling distribution approximates a normal distribution. And so because we can relate this to a sampling distribution, a probability distribution, we only have to take the sample once, and then we relate it back to what distribution is relevant. So trade-offs, right? We could construct confidence intervals up to 100%, but they'd be very wide, so they wouldn't be super useful. We could get wider intervals that would make sure we contain the parameter that we're looking at. Otherwise, if we want a narrow confidence interval and we want a high level of accuracy, we're going to need a lot more data. We need bigger sample sizes. So there's the trade-off between amount of confidence and the width of the interval. What would you do with a confidence interval? Well, suppose your professor is convinced there's no difference between the proportion of a population that's been in a foreign country and then is not. That is, he or she supposes 50% of college students have been out of the country. We obtain a random sample of 100 students, 45% have been to a foreign country. Does this disprove the hypothesis? Well, we could do a same survey of a different campus, a different group of students, and find that 20% have been to a foreign country. Does this disprove the instructor? So remember, different samples give us different sample statistics. So a value that's not in a confidence interval can be rejected as a likely value of the population parameter. So if our sample is within that, then it's possible that it's just sampling error and that sample statistic is close enough to the population parameter. So a value that is in a confidence interval is an acceptable possibility for the value of a population parameter. When a confidence interval for a difference between two parameters, such as two means or two proportions, does not cover 0, then it's reasonable to conclude that the two population parameters are different. This is what I was talking about a couple minutes ago. If your confidence interval is a difference between and it covers 0, it's possible those two groups are the same. If your confidence interval does not cover 0, so it's all positive or it's all negative, then there is likely a statistically significant difference between the two groups that we can extrapolate to the greater population. So confidence intervals, hypothesis testing, we're really looking at not just a single point estimate, but we're looking at the fact that sample statistics vary. We're not taking a bunch of different samples, but we're tying the sample to the sampling distribution to help better get an idea of what is a reasonable range that the sample statistic would fall in to say, okay, this is what the population parameter is like. If our sample statistic is too extreme, perhaps then what we are thinking that is happening with the population parameter is not accurate. That's ultimately where we're trying to go with this information. When the confidence interval for parameters in two different populations does not overlap, it is reasonable to conclude the two population parameters are different. However, if the intervals do overlap, no conclusion could be made. So when we get to hypothesis testing, we'll talk about rejecting the null hypothesis. That is, the information we got is so different that what we understand or what we think we know about that is wrong. So if it's different enough, we can say this is not right. We reject the null. But we never actually accept the null hypothesis when we get into hypothesis testing. And that's because if we look at here, if the intervals do overlap, if they're similar enough, they're within that confidence interval for differences covers 0, we can't draw a conclusion. We can't say, yes, this is right. That's because it is quite possible that the sample size wasn't big enough to detect the difference. Okay. And so when we look at hypothesis testing, we'll talk about rejecting the null hypothesis or do not reject. That doesn't mean we're accepting it. It's simply that it could be that it's true, or it could be that we don't have enough information to detect what we're trying to detect. Confidence intervals are based on the central limit theorem. So our ability to do this inference really comes down to the central limit theorem. And so we can look at our sample statistic averages using the z-score we talked about previously. We can also do it with population sample proportions, percentages that fall into different categories, because they're both allowing us to apply that central limit theorem. So in the next couple of videos, what we're going to do is we're going to apply this information to create confidence intervals for means. So that's where this is going to come into play. And then we'll look at confidence intervals for proportions, which is where this is going to come into play.